Hello, everyone, and welcome. I'm Becky Grimshaw, and I'm Assistant Director of Manchester Communication Research School and Science Leader at Manchester Communication Academy. In this session today, we're going to focus on something that's at the heart of great science teaching, tackling misconceptions before they take root, and how we make being aware of common misconceptions part of everyday teaching practice. We'll be weaving together two powerful approaches: the EEF's radar model and structured oracy strategies inspired by Voice 21. By combining careful planning with purposeful student talk, we can make misconceptions visible early and help students to build a much stronger, deeper scientific understanding. Let's get going. Let's start with a quick reflection on our everyday classrooms. How many times a day do you hear something like heavier objects fall faster than lighter ones, or makes energy? Misconceptions are everywhere and they're incredibly persistent. Students can hold on to them stubbornly even after a topic has been taught. The EF Guidance Report for Improving Secondary Science really emphasises that learning science often involves unlearning intuitive but incorrect ideas. If we ignore these misconceptions as science teachers, we risk the students building shaky knowledge on top of weak foundational knowledge. So, addressing misconceptions early isn't optional, it's essential for real understanding. The good news is misconceptions are often predictable, and the more experienced the teacher becomes, the easier it is to predict and identify the misconception for a topic. Research and classroom experience shows us patterns in what students build their misconceptions. For example, in physics, students often believe heavier objects fall faster. In chemistry, they may think that particles expand like balloons when heated. In biology, many believe plants eat soil or sunlight directly. If we anticipate these misconceptions before we teach, we can plan lessons that meet them head on, instead of finding out weeks later that they've taken root. But why are misconceptions so stubborn? It's partly because students rely on everyday experience to make sense of new information. Their intuitive reasoning often seems obvious to them, even if it's wrong scientifically. Our brains seek coherence and we like things to make sense quickly. Scientific explanations, especially the abstract ones, often challenge that comfort that we like. So, unless we deliberately confront and replace misconceptions, students will simply bend new facts to fit their old incorrect ideas. The ES radar model offers a structured approach for addressing misconceptions systematically, and we can split this model into three parts. The first is research and anticipate. What are the common misconceptions, and when might these emerge in our classrooms or curriculums? Diagnose and address. How can we show our students thinking early, and what strategies will we challenge and rebuild these ideas? And thirdly, assess and review. How will we actually know that change has happened? Today, we'll walk through these steps, and importantly, we'll look at where to use purposeful student talk to strengthen these steps. Our first task when we're planning to teach a topic is to research and anticipate. Before introducing new content, it's important to explore the likely misconceptions that students may hold. This can be done using a range of sources, such as the EF Guidance Report, Best Evidence Science Teaching Resource, and the insights drawn from your own and your colleagues' classroom experience. Once you've identified potential misconceptions, you can then deliberately plan tasks that invite students to reveal their initial ideas. These tasks should allow you to hear and understand the mental models that students are using, even if the students themselves aren't quite fully aware of them yet. This could be done through diagnostic questioning, short written tasks, or even casual classroom talk to ensure that learning builds on secure foundations. We'll look at some specific examples on the next slide. When conducting your research, consider the following questions. What prerequisite knowledge is needed for students to access this topic? Can you consult collections of common misconceptions, past examiner reports, or draw on professional experience of your own colleagues? What's the vocabulary for this unit? Are there terms that students might find confusing? Which concepts from previous topics directly link to this one, and how can you make these connections explicit? How will you revisit and build on those ideas? And how will you activate and assess your students' prior knowledge? On the screen, you'll see an example of research gathered for two specific science topics. These examples come from the EF website under the Improving Secondary Science Guidance report. You can see how the research may differ between topics and what information for each you may need to think about. The purpose of a diagnostic task is to allow you to get an idea of the model students are currently working with. There are usual tasks that can help with this, such as multiple choice questions with non-examples, or explain your thinking tasks, like short written explanations to reveal hidden misunderstandings. But we know that oracy is a powerful tool, and this part of the diagnostic framework isn't just about quizzes or tests, it's about listening to students who are thinking deeply about a topic. Oracy techniques like concept cartoons, which you can see on the screen, which show a picture where characters voice common misunderstandings and ask students which one they agree with or disagree with. Silent summarizers, where students rotate as a speaker, listener, or summarizer. Or just discussions with structured sentences. Is it true that heavier objects fall faster? Can all allow students to show half-formed or contradictory ideas that written assessments or tasks often miss. These structured taught tasks have allowed us to catch misconceptions while they are still elastic enough to correct. Next, we move into the addressing misconceptions through oracy. Modelling oracy is still part of oracy. Once we've surfaced misconceptions, our next step is to actively and thoughtfully challenge them. The goal is to help students unlearn, unpick, and rebuild their understanding based on the ideas they bring to the classroom. We can do that through targeted questioning and modelling. Questioning in this situation is a vital tool. Encouraging students' questions allow you to address and explain the misconception while you model the concept. For example, asking, why might someone believe that? Or what's a non-example of this? Rather than simply giving them the correct answer, we can guide students through the process of that conceptual restructuring, using dialogue as that key tool. This dialogue comes from you as a teacher asking the right pre-planned questions to direct the mental discomfort, allowing for that conceptual reconstruction. We can also use predict, observe, explain. Sometimes, using the advantage we have as a part practical subject, we can redesign practicals both as a demonstration or a class practical to reveal the gap between what students expect and what actually happens. In these situations, we can create discomfort needed for the change in thinking to happen by getting them to first predict. Students commit an idea by sharing what they think will happen, then observe, so they'll watch the experiment or demonstration, and then explain. They'll reconcile the outcome of that scientific reasoning. Again, using targeted questions carefully, we can guide the discussion and thinking around that. The power of this structure lies in the cognitive conflict. When the outcome doesn't match the student's expectation, it creates a moment of emotional and mental discomfort. And this discomfort is often the catalyst for making that real conceptual change. The third thing we need to think about is the role of language in shaping understanding. Sometimes, without meaning to, teachers reinforce misconceptions through the imprecise language. For example, energy is used up instead of energy is transferred from one store to another. That small shift matters because language frames the way that students construct mental models. Precision is crucial. Even subtle changes in phrasing can have a significant impact on students' understanding. To help students truly understand, we must surface misconceptions, create productive conflict, and guide them through the process of rebuilding ideas. Precision, structure, and language all play key roles in this journey from confusion to clarity. As teachers, we use a range of formative assessment strategies, such as low stakes quizzes, class tasks, and diagnostic questions to check whether misconceptions have been addressed. If it becomes clear that misconceptions still persist, teaching is adjusted accordingly. Affected teachers understand that misconceptions are often sticky. They don't just disappear quickly, and they may resurface even after students initially appear to understand. That's why it's important to test again after the forgetting gap, when students have had time to process, forget, and reconstruct their ideas. This reveals whether a student's understanding is truly secure. Assessing whether a student can repeat an answer is not enough. What we really want to know is, has their mental model genuinely changed? To find out, we can use oracy as a deeper, more diagnostic strategy. Re-explanation Re-explanation tasks, like the one seen on the screen, can help reveal the clarity and depth of their new understanding. Listen carefully to language as you circulate your classroom. The words that students use often say more than multiple choice tests ever could. Their phrasing reflects how they conceptualise their ideas. Returning to tasks after time, say weeks later, and ask them again to explain their topic. This is particularly useful if the information is needed to access the lesson. You can see in the example on the screen, this is a discussion around an exam question, but it allowed students to revisit and reinforce a concept. This could be useful to check for lasting change and not just surface recall. To ensure misconceptions don't re-emerge, we must revisit and reinforce key ideas over time and embed them across the curriculum. When planning lessons, consider when and how you will revisit key concepts and misconceptions from this topic. Where can the ideas from this topic be reviewed or referred into future units? And how could you assess understanding of the most common misconceptions in the future? You don't have to redesign your whole curriculum to start applying for these strategies. You could start today. Research one common misconception in your next topic. Plan one oracy-based diagnostic activity. Focus your questioning on challenging and deepening a student's thinking. These small adjustments, when made consistently, transform student understanding over time. Before we wrap up, I'd love you to reflect. What's one misconception you know is common in your subject that you can tackle differently next week? Just take a moment to note it down for yourself. For further exploration in this area, there are a few key reports and places. The EF Improving Secondary Guidance Report can be found on the EF website and has a range of resources to help support the implementation of the recommendations on the report. Voice 21 Oracy has lots of information and evidence-based strategies to help support oracy into the classroom. Best Evidence Science teaching materials from the University of York have the wide range of information on common science misconceptions and diagnostic tasks to help you reveal these. Thank you for joining today, and if you require any further information or support, please don't hesitate to get in touch. Thank you.